Okay, welcome to the November NWCPP meeting. Our speaker tonight is Chris, so I'm going to go ahead and just turn it over to him. And he's going to be talking about 3D graphics for dummies. All yours, Chris.
Okay, I shared the screen. I hope you can all see it.
Yes.
Okay. First, a caveat, significant content borrowed, quote, from Dan Chang at NTD Nintendo with permission. I asked him when I was originally going to prepare this talk about a year ago and said, it's okay if I use some of your slides? And he says, yeah, sure, go ahead. So I'm taking that as permission. So how do you draw 3D graphics? These all look like nice, smooth objects and stuff, but they're really not. They're a whole mess of triangles. And you can simulate just about any shape by making a whole bunch of triangles, sometimes also called polys or polygons. So that 3D shape we were looking at a second ago of the pill shape, the box, and the sphere, you can basically make a whole bunch of triangles to fill that in. You can also make things that are other than inanimate objects. You could do something like a dolphin, a whole bunch of triangles. The more triangles, the better resolution you get. You can do something that looks like a stealth fighter, with the flat edges, or divvy up all the triangles smaller and smaller and smaller until you finally get down to the end. This one, which is pretty smooth. You've probably seen a lot of wireframe objects like this with squares. Squares are a little bit hard to deal with when you go to draw them, and I have a slide for that in a minute that will explain that. The way around that is you take every square and you cut it in half and you make two triangles out of it. As you all remember from your probably fifth grade geometry, a plane is defined by 3 points. If you bring a fourth point into it, you're not guaranteed that it'll be on the same plane, and it makes it really hard to draw and to wrap a shape across. So a little bit of side peripheral stuff. A model is an object with surfaces. At this point, we really don't care about the inside because in theory, you're never going to see the inside if it's a closed shape. And the way that you would make this shape into a whole bunch of triangles is just to cut it up. And so you then get each surface that has an image on it, you would cut up and you apply the math. Pardon me, that this object, this triangle will map to here. This triangle will map to this part here. A tricky little thing that can happen with these surfaces is you have to put them on there face up, or you will actually be looking at the backwards. And the way to keep track of that is there's a right hand, left hand rule, and there's also called winding. So on our surface, or also sometimes called the texture, you have 3 points that define the triangle. In this case, I called mine S0, S1, S2 for surface. And then P1, or P0, P1, P2. If you map the S0 through 2 to P0 through P2, it comes up forward. If you put it onto a shape and you do it backwards, it rotates the opposite way around. So if you put your fingers out using, for example, your right hand, and you bend your fingers in the direction of the order of the points, your thumb will point in the direction that is up, or that will be towards the face of the image. So in this side, we're turning the same way. In this side, I hope you can see my mouse pointer pointing on here. This piece. Oh, you're not seeing my mouse?
Yeah, I can't see it.
Okay.
Probably your mouse pointer is on a different screen.
Do you see the mouse pointer here?
Yes, now I see it.
Okay. So sorry about that. Thank you. The P0, P1, P2 if you bend your fingers in the direction that's going, up is pointing into the cube. Because what it does is it takes and flips this picture around in the direction of the curl that it's going. And it's easy to get that confused, and I'll show you an example of that later, what it's happened. So each model has a matrix that defines its position in the world, orientation in the world, and specifies the scale. That's really three separate matrices that you multiply together, and we'll get to the matrix math in a little while. There's a series of transitions that happen that when you take your model, which is in its own coordinate system, that probably has origin in the middle of it, you move it to the position where you want it to, you twist it, and you grow it to the size that you want. And so the model, you transform it into world space. Then you apply view space to it, and you can see how it twists it a little bit. So if this were a cube, we twist it to position it, and then it gets torqued for our point of view. And then when you go to convert it into screen space, it gets perspective. The front surface and the back surface are the same size, but because the way you get vanishing points, the object, the surface that's behind is smaller. So it's the perspective of how you would see it. So each model has its own X, Y, and Z. But what happened? I just went to the end. I have to go back to the top. Why did it go all the way to the end? Sorry about that. People? Ah. Okay. No, I did not go back far enough. Sorry. What? Hang on. Okay. So model space, each object has its origin, its X, Y, and Z direction. Then you can take multiple models and copy them and put them in the world, which is oriented by X, Y, and Z. This diagram shows a light source. I'm not going to address that. That's more of a little bit of an advanced topic, but you can see how the far sides from the lighting source would be dark. Then what you do is you take this world space and you convert it into the view space. The coordinate system changes again, and we get a little bit of a, not quite a perspective yet, but we're looking at it from an angle. A little bit more complicated is the screen space. Imagine you have a camera and you're looking into your world space with everything, or into your view space. So your coordinate system, and this entirely depends on which application you're using, but X, Y, and Z, and the back plane, you can see through a small window at the front, but the back would be a little bit larger window. There's a clipping technique that will clip out anything that's closer than the front pane and clip out anything that's further than the back plane. We'll address it, but I won't give all the details necessarily. So this converts us to our coordinate system. So we're looking at it from the screen space. Then we apply the perspective at it, or pardon me, this is the view space. Then we need to apply the point of view to do the perspective. We give it the point the camera's coming from, where the camera's pointing, and the up vector. The up vector is important because imagine you have a camera and you're shooting a scene, and you've probably all done with your cell phone, and you have it turned sideways. The image on the screen looks right, but you're really recording it twisted. So if you kind of do a pointed finger, I'm not sure if you can see my hand clearly or not, but you point it where you're looking at it and the thumb is pointed up. But if you point it sideways, your image that you're going to be looked at is sideways. So that gets torqued. And the projection matrix is that the field of view that we get from when we're looking through our camera. Field of view is the view in the y direction. Aspect ratio is the width divided by the height, so you get your scale of your window correctly. You get your near plane and your far plane. And I'll cover more of those in exact examples here in a little bit. A couple more primitive things that are handy to know. Everything is made out of points and vectors. A point is just something that has an absolute position, and a vector has a direction and a length. Vectors aren't at any particular spot, whereas points are. There's some mathematical differences, which we'll get to those. For keeping track of them internally, points internally are written with a 1. This is an x, y, z, and this parameter is called a w. So the w parameter for points is a 1, a vector is a 0. That way, when you do matrix math on it, you can look at the end and see what that value is. To remember if what you were dealing with originally was a point or a vector. Almost all of my examples I'll be dealing with will be points. And my math library that I wrote for my matrices knows if you're dealing with a point and you'll multiply it by a matrix, you will get a point object back. But if you're dealing with some other library that didn't keep track of them for you, that's what you get. When I originally took this class from Dan Chang, when he offered it several years ago where I was working at Nintendo, he was having a hard time keeping all of his math entirely straight with points and vectors and matrix multiplications. So he heavily relied on this 1 and 0. I wrote a math library that is type consistent, type coherent, and so you won't have that much of an issue. A couple other things about points. When you subtract 2 points, you get a vector, the length of the distance between them. When you add or subtract 2 vectors, you get 2 more vectors. You cannot add 2 points. That's just 2 positions. So vector addition, you get V1 plus V2 is the same as the hypotenuse here. So this is V1, V2, or V3. Just going to add them head to tail. Straight X and Y, Z math, you just add all the coordinates together, the X, the Y, and the Z, and you get what your new vector would be. I'm going to be skipping a lot with vectors, some math and examples and stuff which is handy to know, but not necessary for the introductory to graphics. I'm going to be skipping a vector times a scalar, calculating the vector length, how to normalize a vector, vector dot product, vector cross products, and a reflection vector. The reflection vectors are real handy when you're working on light sources and how much is making it to the camera's eye. Triangle and plane normals, I'm not going to address either. The plane equation or how to square up vectors. Internally to my math library, I use it in 1 or 2 places, but we won't need to address it here. But these are things, if you want to get deeper into doing 3D graphics, you'll need to understand. Different graphic systems. Unity does a vertical column to describe vectors or points, where a point would have a 1 in the last. Monogame, which is a C++, or pardon me, a C# engine, the mono flavor of C#, it does coordinates out this way. I don't really use either mono or unity, but I write out my coordinates horizontally. It just makes a lot more sense to me. Matrix math, and going back to what you probably did as a freshman or sophomore in high school, to multiply two matrices, they have to have one common dimension. So this is a 4x1 and this is a 4x4. So the 4 and the 4 match up. To go through and multiply them to create a new vector or point, you take Vx times M11, Vy times M21, Vz times 3,1, W times 4,1. Do that for all the rows, add them up, and this becomes your X, your Y, your Z, and your new W. My library that I do keeps track. It has a matrix. It's hard-coded at 4x4 for all the math I'm doing. I don't need to do anything beyond that, so it's a lot easier to hard-code it. Vectors are 1x4, X, Y, Z with W equals 0. Points, there's a 1x4, X, Y, Z with a W of 1. A mesh is a common term in graphics of when you have a collection of polygons or triangles, and that, along associated with each one of these polygons is the surface associated with it. And then you have you got your mesh of your object, you got a mesh for your world, your view, and the screen. They really are all the same object. For type sense, I actually do a using. Just some of the meshes get more and more complex with more and more objects in them. The mathematical operators I define, you multiply matrix times a matrix, either do the unary form or the simple form or the spelled out form. Vectors, you can multiply a vector by a matrix. The first two examples give that. You can multiply a vector times a vector, and that gives you the cross product I talked about. I wasn't going to talk about those, but I do have that. This is also a cross product. And then how to normalize a vector. Again, we're skipping that. Points, I can multiply a point by matrix, point by matrix. I can add a point in a vector, and that will take the point and move it the distance of the vector. Also another way of doing it. And I can subtract 2 points and create a vector. Whoops, we've got more to cover here. Meshes are, so I can add multiple meshes together and create a new mesh, or I can add another mesh to it. I can multiply a mesh by a matrix, and what this actually does is it goes through every point that's inside the mesh and multiplies it by the matrix. And you'll see why we're doing the matrix multiplication here in a little bit. I also have a perspective divide. That is not strictly a matrix operation, but it's a step necessary for converting to the actual screen coordinate system. There are several predefined formulas for creating a matrix that you can then apply to an object. This is just a stock form of, I want a matrix that will give me a rotation of X in so many degrees, Y in so many degrees, Z in so many degrees. And the scale is how much you're just going to blow up or stretch each axis, X, Y, and Z. And translate is move an object over X, Y, and Z. I also have my point of view, field of view, and viewport matrices. Cover those a little bit more later. Here's scaling. You just each axis is just stretching for these. And this is a very simple matrix. You just substitute X, Y, and Z, and you multiply it. Again, my library does it for you, but this is internally what that matrix looks like. Translation would move an object over. So in this case, it moved it over 5 up to, and nothing on the Z. And that's just substituting the terms in here and then multiplying it across. Z rotation, some sines and cosines and some arguments you substitute in, and you would multiply your entire object, each point in your object, by this matrix, and it will come out in the new rotated form. X works very similar, and the rotation of Y works very similar too. There's something, an object, a mathematical term that I'm not using or doing in here, but it's something very handy, and you need to know that it is capable of doing it. Something called a orthogonal basis. Every world has its own X, Y, and Z. But many times you end up creating a world that's in one set of X, Y's, and Z's, and you want to take those points and convert them to imagining that there's an entirely different coordinate system, and you can convert those from this X, Y, and Z to a NVU coordinate system. So one point that would have a number here would now have a whole new, the point would be in the same spot, but it's using the numbers associated with it are on a different axis now. And this is around the origin at what would be the 0, 0 for both of them. If you have a world and you want to convert the coordinate systems from one to another, and their origins aren't at the same point, you need to do a translation or a move your entire world such its origin lines up with the origin of the other one. Apply the orthogonal basis matrix and then move it back. The matrix for that, and it's amazing that this actually works, you just plug in the vectors into each of these, multiply it across, and it magically works. Okay, for matrix multiplication, you can take a vector or a point, multiply it by a matrix, and then multiply that by another matrix, and multiply that by another matrix. Remembering that this multiplication returns a vector, so this would be this creates a vector times a matrix, which gives you a vector, times a matrix gives you a vector. It reads in this order: V times M1 times M2 times M3. You can also multiply these matrices together. So if you have a whole bunch of vectors or points you're going to apply this to, you only have to multiply these matrices once, store them as an individual matrix, and then apply them to each of your vectors or your points. So that way you don't have to do this math over and over and over again. You just have the matrix is the product of these and apply that to there. Or the order of the matrix is important, because if you want to translate an object and then move it, or pardon me, then rotate it, you actually need to rotate it first and then move it. Because if you don't, you end up with this problem. If you rotate and then translate, so it rotates the 45 degrees and then it gets moved over. But if you do it in the wrong order, you move it over and then you rotate it by 45, it's rotating about this matrix, or pardon me, about this origin. So it's actually going to be moving it over and then rotating it up. So it's going to be entirely in the wrong position, unless that's what you really wanted to do. Probably wasn't. So you need to do them in the right order. So you'd multiply by the matrix for the rotation and by the matrix for the rotation, or pardon me, for the translation. If you do translation then rotation, it will probably end up with what you're not looking for. Okay, we've seen this slide before. This is pseudo the pipeline. We go from model space to to world space, to view space, to screen space. This is also in this pipeline. You multiply your matrix, your model times your matrix for your world. Gives you world space. You take your multiply that times the matrix for your view space. You multiply that by the projection. Multiply that by you apply the clipping. This is actually an optional step where you have to go through and examine every point and throw out the ones you don't want. You multiply by the view space, and then we have something that's called divide by W. And we'll see that here in a little bit, and why that is and why that works. So here's an example of some matrix multiplication. If we wanted to rotate our object 30 degrees and then move it 100 coordinates over on the Y, we would take each of these matrices and we could just multiply them together. That gives us our one matrix that we would have here, doing two steps in one. And so this is what the matrix is that we're calling our world matrix. If we had a set of 4 points, then this kind of forms a square that is bounded by plus and minus 1 on the X and the Y, and just sits flat on the Z. We go to multiply it by this matrix, we would want to get this. But remember, this is a 1 by 4, or probably 1 by 3. You cannot multiply that times a 4 by 4. That's where our padding comes in of the extra digit for the W. And this is a point, so it has a 1 is the in the W position. You do matrix multiply these coordinates by our world space transform, and we come up with these funny looking numbers. Then we would take the convert the point of view from where we're looking at our world into a view matrix, our camera position, our camera target, and our up vector gets us this. We go to multiply the points we had before, these points, by this matrix, and it gives us these points. And this is how kind of the world, when we're in world space, we're here, but if our camera's here, pardon me, I'm pointing at the wrong screen. So this is our world space. And if the camera is here, when we go through this transform, now the camera is the center of the world, and we're rotated and shifted, and we're looking at this down from an angle. So this is what the world space would look like, but from the perspective of the camera. Of course, you have to imagine yourself out of the space of the camera, but that's where the view Fulstrom comes from. This is the camera looking at our world, and we need to apply, we've seen this slide before, our front clipping, our back clipping, and it expands out. So our field of view is 45 degrees, our aspect ratio, and this is whatever aspect ratio your window is. So 1 to 1.3, 1 to 1.3, which is basically a 4 by 3 screen. The near panel distance, far pane distance, substitute into this field of view formula. It gives you that the projection matrix. We saw that field of view before. I'm not going to bother with the equation now, but this is what the matrix comes out to be. Multiply your 4 points by this matrix, and it comes up with some more really funny looking numbers. If we were to do clipping, we would look at the W value of the point and make sure that X fit in a valid range there, and the Y fell in the valid range, and also that the Z was between 0 and our W value. This means anything outside of the PW, the point, the W parameter in the point, is going to be outside of the view of what we're going to be looking at. I didn't bother to do that with mine. I kind of do that in a step later. This is the viewport scale matrix. We substitute our values in. And of course, I have my library does this for you. But the width was 640. We divide that by 2. We substitute all these values in for height and width and our front and back depth. We take that matrix. We have our funny 4 sets of points that look like total garbage at this point. Multiply by this, end up with something else that looks like more total garbage. Entirely really weird. Then the divide by W. We go through and we divide every value, the X, the Y, and the Z, by W. So this is the W you divide into each one of these. And so 9.74, 10.59, yada, yada. Divide each argument there by this, and this is now your screen space. These are much more reasonable values for what you would expect to see on the screen. If you take just the X and the Y values, that is the X and the Y values that it will fit on your screen as it was flattened out on your 2D. The Z becomes the depth, how far back that point is away from the screen. Depending on your world and what you set up as your perspective, these numbers may be greatly different. For the example points, this works out that it happens to be between 0 and 1. So the blue point is the blue point here, the green point's here, red is here, and black is here. So that takes what was originally a rectangle or a square that was bounded by plus and minus 1 on both X and Y, twisted it and moved it around, did things to it, and now we're seeing it at an angle. The green point is furthest away from us. It's a 0.91, and the red is closest at 0.88. And that was, of course, we were on a 640 by 480 window, as we had put into our math before. Okay. This is the next subject is something that really bends a lot of people's minds, and they can't. This is what makes 3D graphics a little bit complex. Say you have a world and a bunch of objects you dropped on there, and they're in front of each other. The sphere's in front of the cylinder, the teapot's partially in front of that, the dodecahedron's in front of the teapot, the cone's in front of the cube. You can't draw all of the cube and then all of the cone, because you end up with problems with it. The way that most systems handle this is a Z buffer. They go through, and remember, these are all made up of lots of different triangles or polygons. You take each poly and you iterate through every point on every surface, you rasterize it, you look at the W or the Z parameter to know the depth, and you convert that into a grayscale. And the further the object away is, the lighter it is, the closer it is, the darker it is. So you go through each of the polys in here. So there's probably a triangle here, and that all turned out to be this gray beige. The 2 triangles here, which would map to roughly here, and part of it is obscured by this cone, but if we've only done these 4 polys so far, here, 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 and here, they're light. When we come along to this cone is probably made up of hundreds or dozens of triangles. We go to draw each one of those, we look at the point and we see, is the point on this surface further away or closer than what was previously drawn? If it is closer, we draw it into an image buffer. And these image buffers, there's normally a way of toggling, switching what you're viewing, so you don't actually see all the drawing and everything flashing on the screen. So you have this image buffer that's off screen that you draw into. So if this purple point in this poly right here is closer than the surface behind it, so right here near it's darker it is, so we would draw it. Actually, let me actually back a step. Say that the green triangle is drawn first. We would actually draw that in because there's no other object that's closer. Then by the time we get to the cone shape, we realize it's closer. It overwrites what was previously drawn there. Wasted cycles, but it's easier to do that. So you go through every poly on every one of these objects, and then you would blast that onto the screen. Windows terminology, it's a bit blit. And then you draw your next one in your next image, in your alternate image buffer, and draw all those in. Oh, Z buffer. So I kind of already described the whole operation on that. Now, we talked a little bit about surfaces, or what are also called textures. This point maps to this point maps to this point, this maps to this point. Basically, take this object or this surface and you twist it in space and you glue it on the side. But that requires stretching and distorting this shape. So we have this triangle here, which is what was originally a regular triangle. We can, if I cut out and just localize just on this, and the way my rasterization works is it's mathematically easier for me to cut this triangle into two separate triangles. And you'll see why that works. We know the depth. We know the X and the Y at each of the corners, and we know the depth at each of the corners, but we don't know what the depth is in the middle here. Pardon me, I'm pointing at the wrong screen again. So we know the point, so X and Y in the depth, X, Y in depth, X and Y in depth. So I cut it in half. But we do not know what the depth is in the middle of this object. So this could be a really massive object that would cross and collide with lots of other objects, or it could be really small and not hit any of them. The way to calculate what the depth is in the middle of this object, and actually for rasterization, let me back up half a step. Rasterization is you take this and you slice it in rows of pixels all the way across from the top down, scanning across. So as we're going down, I know what my depth is here, and actually I'll go ahead and do here. This green line is the raster I'm working on now. And so I have this interpolation of how far apart these are between P1 and P2 is the distance from P0 to P1, and then my new P1 here. So this is D1 prime. I can calculate the distance at this point. Stop that. At this X and Y. I can also calculate the point here, and what I do here is I know this triangle's equation, the slope of this line. I take the Y, calculate the point here, and that gives me my coordinate here. I can calculate what my depth is here by interpolating between, stop that, it doesn't like me clicking on it, the depth at this point and the depth at this point, and interpolating based on how far apart this distance is. It gives me the interpolated depth here. Then as I scan across each pixel in this row of pixels, I can then again interpolate between the depth of D0 prime and D1 prime. And actually I changed my nomenclature, sorry about that. This should be D1 prime and D2 prime. And then this is an interpolation again. That gives me my depth at this point. At that point, or then I do the same thing for my bottom triangle, but it's a different set of interpolations. It's between this point and this point, and this point and this point. I potentially could have done between this point and this point, the interpolation here, but it works out not much nicer math for me to continue interpolating across the whole hypotenuse here and this ratio, this position here, and scan across each pixel here, and that gives me the depth. Once I scan across every pixel, every row, and every pixel in every row, I compute a depth. Then remember, the darker it is, the closer it is to you. Then actually back up here. You can use any system for this. You could have said lighter is closer. You just have to be consistent all the way through. Same as far as the orientation of the X, Y, and Z axes. Different game engines will use different coordinate systems. You just have to stay consistent within that gaming or drawing engine's mechanism. So this point is closer, right? This point is closer, this point's further away. Okay, now applying textures doing rasterization. We've seen this picture before. This point matches this point matches, and we twist it and we shove it into there. Zooming in on it, it looks like this image will want to get applied to this surface. And I've already drawn in what the picture is on there, so you can see where it's going to be going to. Again, we cut this triangle in half. We calculate what the points are on here. And then I interpolate across the exact same way as I did for the depth, except for I'm just calculating position now. So X and Y, or interpolate the distance after, pardon me, let me explain this further. Scanning across every row, every pixel in every row gives me my Y coordinate. And then as I'm going down, I go across each pixel here and I get interpolate here. So I take this interpolated ratio to this height. These don't need to be in the same coordinate system. They're all relative to each other. So this ratio here to here to here gives me that maps the same point on the edge here. Same with here of this interpolated distance, calculates that the point is here. Then I need to step evenly, or pardon me, I go evenly across each pixel here in this row that I'm on. I get the interpolated distance. I do a 2D interpolation between this X and Y and this X and Y, do this distance. Then I look up the pixel that's at this point. In this case, this point would be yellow. We would have painted yellow into the image buffer. Now this is for the upper triangle. Same thing for the lower triangle, but of course we're dealing with the ratio of this side to this side, and I'll still continue it on using the same hypotenuse and scan across every pixel here, looking up each point in here for the color and then painting that into the image. That applies the surfaces to the sides. So this would have been the triangle we were drawing in this case. So this would be actually done 11 more times. 2 triangles for every side for this object, plus there's ones on the back that we need to compute because we're doing the grayscale distance. There's polygons on the backside of the triangles, which we also computed the distance for and had to check to see if they properly were in front of or behind the depth of the object that was there before. There is one problem in using triangles when we're doing this. If we have a grid object like this and we have a triangle here and a separate triangle here, and we go to map it onto an object, a square, which had been twisted in space and at that angle, and as we go to apply it, and we're scanning across each position here to paint the dots here, we basically go down each one and we go from and here's where the error becomes visible. The 10% point to the 10% point on the hypotenuse, the 20% to the 20%. Makes lots of sense if we scan across, but This triangle here is deformed, and this triangle is deformed. The 10% on the side here to 10%, and I'm talking in percentages because we're doing the interpolation between the sides, is to there, and so it draws to there, 20 to 20, 30 to 30, 40 to 40. And also the other triangle, when it draws, it does the same thing. As it goes to paint in this triangle, it stretches and applies this into this region. 10% to 10% on the hypotenuse, 10% here to 10%, pardon me, 10%, 10% to 10, 20 to 20, 30 to 30. But as you can see, there's a little fine white line that I drew in that is, oh, stop it. My mouse does not like me. This creates an artificial line of perspective of all the white lines. They're parallel to each other. What we really want is for the edges, this edge would go back to a vanishing point. This edge goes back to a vanishing point. In theory, all of these points should be on these lines in the grid should be on the blue line, so they each also go to their to the same vanishing point. This is a drawback drawing with triangles. Had we been drawing with rectangles or squares, the 10% here would be 10% here, 10% here would be 10% here, and these lines would be straight. However, because of the previous problem I mentioned of you can't guarantee that all 4 points are going to be on the same plane, it's a compromise we have to make. There's a much more complicated math of actually doing a reverse matrix transform from what our final pixel position is back into what the original triangle was, then scale the triangle to fit into that, and then take that color and apply it back. It's a heck of a lot of math and really, really slows things down. Most of the time, you won't see this in dealing with triangles. If you're dealing with lots and lots of smaller triangles, this isn't as much of a problem. But just know that there is a math issue with it. And there are lots of different names with it. Affine perspective error with poly interpolation, or derivative discontinuity in interpolation. Basically, it just means things don't line up because the math bent them. And the reason, and actually, I skipped a word earlier here, this triangle knows nothing about this triangle when it's going to draw. If it didn't realize that these two lines pointed back to a vanishing point, you could compute that. But these two polygons, this triangle here and this triangle here, are two entirely separate polygons that are just dumped into the same mesh together. They don't know they're next to each other. Okay, for my sample little app, I take a set of 3 coordinates to define my triangle, a image ID of where I'm going to get my triangles from, and these are the coordinates within this triangle. And so the 0, 0 to 0, 179 to 179, 79 and back, this is one triangle, and this is the other triangle. Because of winding, when you go around this way, it works easier if you also continue going around the same way. So notice I start at 179, 179 to 179, 0, and back to 0. Keeps the winding much more organized, but you'll see there's actually an issue with the model for the up that I've done later. So this uses one bitmap image 12 times. And I apply just 2 triangles from that each time. I don't have to have the same thing on every side. I could actually use multiple different triangles, and most of the time in a complex object, you'll see that. Say as in the rabbit or the dolphin we showed the picture of earlier, each one of those would have a slightly different texture of what the fur looked like or the skin looked like, and different lighting and shading. So one of those might have hundreds or thousands of what that each particular part of the image would look like, what the fin looked like, the blowhole looked like, whatnot. But also use just one image and cut up 12 separate triangles to wrap around a cube. I take it you recognize that this is going to be a square globe with North America, South America, Antarctica, yada, yada. And so these are the 12 triangles laid out here that are in each of these coordinates mapped on to each of these triangles. So we talked about all of these matrix multiplications earlier. This is where this becomes extremely simple. And this is just a sample piece of code of what I have in my little sample app. I have the rectangle of my screen. I have what my model looks like, and then some parameters of what angle am I going to rotate it at, how much am I going to scale it, grow it up or down, and how far am I going to offset these, and I'll explain that in a second. So basically, I take my original model and I scale it, I multiply it by 5 by 5 by 5 by 10 by 10 by 10, whatever. I make a copy of the model and I rotate it the z-axis by 90. And then I take another copy of the model, I rotate the y-axis by 90, and I get 3 different models here. I have my world. I take my model X, I rotate it again, and once it's rotated, then I shift it into the minus minus quadrant. I take the model Y, I rotate that the same angle, but remember I'd already rotated up here too. I transform this into the minus plus quadrant. Oh, I also push this one back 20, this one back 40, this one back 60. Do the same thing, Z into the plus and minus quadrant, and then I rotate on the X, the Y, and the Z. And remember, this is actually doing them in this order. Both it's rotating on the X, then the Y, then the Z. You can't do actually all 3 at the same time, or you would make the object collapse in on itself, and you would create a black hole. And of course, then this one gets pushed off into the plus plus quadrant and at depth 0. So I got 4 copies of my model in this world, each at different positions and each rotated differently. I create my point of view, my field of view, and my viewport. I multiply all those together. I multiply this times by my world. And actually, I wanted to back up one point here. This model is a mesh. So this matrix multiplication that's happening here is happening on every point in this model, and then that's creating a model that's added to this world. This matrix multiplication is applied to every point in this model and added to this world, which is a mesh. Same for this model and this model. So point of view, field of view, and viewport, multiply them together. That multiplies by this world. This world is a mesh. It goes through and multiplies by every point, and that converts it into a screen object or mesh. Then there's that perspective divide. So this is the 2D not depth taken into account. And I do the perspective divide, which divides the W across every X, Y, and Z of every point in this mesh, and I return a copy of the screen. Yes, this would look very big and bulky that I'm returning an entire object on the stack, and it would have to be copied. But of course, we all know we have return value optimization. When we return an entire object, it actually passes in the object from the outside world, and this doesn't actually really construct it. This initializes my outer object and copies it into that. So it's a cheat that I get to take advantage of return value optimization, and it skips a copy. So I talked about I push things into the 4 different quadrants, and I have them at different depths. The object further away is lighter, it's rotated differently. The next object, and the next object, and then the object is rotated on the X, Y, and Z. This object is rotated about the X-axis, which goes through the middle. This object is rotated through the y-axis, which is at the top. This object is rotated through the z, which is coming out in the screen, and this object is rotated in all three. So this is what the depth buffer looks like. Then we would go apply our actual images to it, and it would look like this. Yellow doesn't make very good distinctions for the edges between objects, but you can kind of see what it's doing. And this would be with the world object, or the wrapped around it. And you can see how it's twisting there. Okay, got a demo for you. Actually, before I go any further, I could have been bulldozing through that. Do people have questions about what I have done so far? Okay, I don't see a or rearranging my window so I can see the chat.
Yeah, Pete's got his hand up.
Okay, yeah, I was trying to figure out who that was. Yes, Pete.
So the question I have is, why do we do the perspective divide? I understand that we do it, but I'm not sure why or what it does for us.
It makes an object show depth, that in a cube, the back side is smaller than the front side. If you have two squares or two pieces of paper, and you hold one up in front of the other and kind of have it at an angle, the one that's further away looks smaller. That's the perspective. It's through some dark arts of math that it works because of all the previous matrices. I do not understand the math on that. And actually, I have a funny little story on that. When I was a senior in college, well, actually, it even goes further back than when I was in high school. But you've all seen The Graduate, where Dustin Hoffman gets cornered by the drunk neighbor who puts his arm around him and says, "Son, let me say one word to you, plastics." Well, I had a drunk relative do that to me at a party when I was in high school, and he told me, linear algebra, make sure you get linear algebra. I got to college, I couldn't fit linear algebra into my senior year. My schedule was just too full. So I conned my girlfriend into taking it for me. Of course, I didn't learn anything from it. I really wish I had got it. So that would have been 30 years more of graphics that I would have understood. And I only picked this up a couple years ago. So short answer is because I said so. That's just the way it works. Is there any more questions before I go into the little demo? Okay. Do you all see the screen with a bunch of wireframe triangles in it?
Yes.
Okay. I don't know how fast Teams is able to broadcast this. Are you able to clearly see these wireframe objects spinning? Or is it being too jerky? Do I need to slow it down?
Looks okay to me.
Slow down.
Okay. So this is kind of what we were drawing there. Each of these objects is rotated and shoved off into their quadrant. This object is around the x-axis. If you imagine a normal x, y, and z, like you would see on a whiteboard. This is the y-axis, so this is rotating around the y-axis. Z-axis is coming out of the screen at us, so we're rotating around here. This object is tumbling on the x, y, and the z. These lines are the edges of the triangle. Normally, when you have a surface, you don't draw the lines. But this is what I use for debugging an object when I'm creating it. This is what it would look like with the surfaces applied to it. And I want to point out, notice it says up, 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 doop, doop, doop. I got the winding or the right-hand, left-hand rule wrong when I did the backside of these objects. I just took the triangles and applied them to sides. And so what we're looking at is, this is the front side of our surface. This is the back side of it, as if our surface we were applying up there were transparency. So we had our model. We also can switch models and go to the Earth model, and you can see it pivot around. This one has had the winding on the triangles on the side fixed because, of course, it would become very obvious if bottom of South America didn't connect to North America, connect to over to Siberia, into Asia and Antarctica and around. Let me introduce you to another shape. This is Frankie. This is my dog I had for the last 10, 12 years, died this last year. And into my drawing routine, we had the angle. So each of the, so I'm pumping and have a timer that's causing this to rotate and draw. I also have a scaling factor is how big these objects are. Now you can see I've made these objects so big, they actually collide. And this line and this line collide. And so you can see this object crosses through this object. So part of this object is closer, part of this object is closer. Whatever the closest surface was stayed on here. These are not hard physical objects, so they don't collide and they can't stop them from going through each other. If you were making a game, you would have to do a lot of complex math to actually calculate what the depth or what the surfaces were, and if you actually had an object colliding with another surface. This is drawing at 48 frames per second, and there is 54 million pixels being computed and drawn in this per second. If the model is a little bit smaller, turn down the scale, we get up to about 65 frames per second. And of course, because there's not as many things we're drawing, it's 29 million pixels. If I go really crazy and bump this up, I'm losing some off the edge, so those pixels aren't being drawn. And on a bigger screen, this is being drawn on an HD screen. So this is pretty good speed for this rotation. So that's 114, 115 million pixels per second. But of course, more pixels as they get drawn, the frame rate slows down. We're about 37, 36 frames per second. Something else, just to make sure that you understand this a little bit more complex. Every one of these triangles, every single pixel on here is a triangle, and I'm rasterizing every single one of them. So that's like 1,300, 1,400, whatever the coordinates are on an HD screen, lines of resolution I'm going here, and then up to the almost 2,000 across of pixels that have to be cut across. So there's 4 cubes, each one has 12 polys in it, so that's 48 polys going across every one of them that potentially have thousands or millions of pixels in each one, scanning across every scan line here. I have a pretty high-end machine that I'm working on. However, this entire program is single-threaded. All the computations for the rotations of the objects, for the matrix of the matrix multiplications across all the points in the mesh, and then all of the rasterization. It has to rasterize both the grayscale and the color. I happen to do them kind of internested, so it calculates both the grayscale and the color, but which means I'm actually doing more work than I need to, because I potentially draw a pixel and then I just draw over it for if it's in the background. I talked about I didn't do clipping. What I do is when I'm going to rasterize this triangle here, I would recognize that as I'm trying to scan across, that it is off the top of the screen, and I just skip that whole raster line so I only actually draw stuff that's on the screen. Got a couple more models I want to show you. So this is Frankie, and if I do it half and half with the up that we're familiar with from before, these are the triangles for each of the shapes. Now this one's going to damage your mind a little bit, so I apologize for it. If I turn off, get rid of all of the up parts of it and only show the half Frankie, I can actually see through the objects and see the backside of them. And notice that Frankie, in some of these, his nose is going left and other times it's going right. And you can see through to the backside of the objects. This triangle here is the backside as it would come around, but I can see the inside of it because a pixel is a zero depth. It's effectively as if it were a transparency that were painted on there. And so we're seeing the back of it. So if we're really looking at the backside of a surface, he should be facing opposite directions. When he comes around, his nose is still pointed to the same side, but it's shifted off. I want to go back to the previous version of Frankie, and we talked about that interpolation error. And originally I thought this was when I first came up with it, it was a problem of just dealing with perspective of a rotated object. But if you watch the tip of Frankie's nose, it seems to move laterally across it. And also his mouth seems to be closing a little bit and stretching. So it looks like it's opening and it looks like it's stretching. And what that is, before I had understood the whole issue of that, the vanishing point lines in that interpolation issues, I went and made a grid and drew that on a surface and spun that around so I could understand it. That is actually the distortion that's happening because the interpolation is moving back and forth as the angles are at different points. So we have our grid object like we had in our picture before. And as I go let that spin around, when it's square, it's perfectly square. But as things get off to sharp angles, this is having the issue of the 10% to the 10%, 20% to the 20% across the hypotenuse here. Of course, this triangle does not know that this little triangle is pointing back this way. If it did know, you would be able to do some mathematical adjustments and compensation. Potentially, you could also realize that the original triangle you were drawing this from was a right angle, and that this is no longer at a right angle, and do some sine, cosine, heavy math, and do some reversing of the distortion and having these lines go properly off to the vanishing point. See if there's anything else I wanted to show. I did also make it, just because I was worried about the video speed, I adjusted the speed so it could do it at slower speeds. Here's also, we get overlapping intersection of the two different planes and the different depth points on them. I think we'll see another one come across here in just a second. Nope, we missed it. But okay, there, this one's starting to slice into the side there. Okay, I think I've shown you, depth buffer. I have a mode where I actually draw the depth buffer. Let me increase the speed back to fast. And you can see the objects colliding and how the different depth, this front is darker and the lighter portions in the background were gone away. So there's our image. Let's change this back to Frankie. Contrast is easier to see.
Chris, can you slow down? I see just a sequence of pictures.
Okay, let me go. Okay, is that better?
Make the scale smaller. It would seem to work well when they were small.
Well, I actually need to do it for the collisions, but
Can you please set the lowest speed?
Okay. As this comes around, this edge should intersect this face. It's a little hard to see in the small window.
So right now we're getting, or at least I'm getting 0 frames per second. So in the video.
From
I have frozen picture.
I just paused it.
Uh,
Okay, and so I'm going to make it big again so you can see a little bit better. You see this edge intersects this edge, and I'm going to switch back to the depth buffer. And it's kind of hard to see, but there's a little bit of this sharp edge at the front goes down a little bit further, and the colors blend in. I'm going to unpause it for a second and watch it for another intersection. I need to make the scale momentarily bigger, and I'll pause it again in a second when it gets around to an interesting point. Okay, here I have this surface and this surface both intersecting with this surface, and of course you can only see the closer points on it. So when I actually go back to the image, you can see how this surface is colliding with these two different surfaces. Okay, further questions, or people wanted me to go back a little bit and talk about that rendering of the matrix math?
Mike has his hand up, so go for it, Mike.
yeah, so I'm a professional graphics person, but
Good.
so you can fix your perspective problem. So you actually have to interpolate both X, Y, Z, and W over the triangle, and then do a divide at every pixel. And that will fix the texture perspective problems. So you don't divide early on, you divide, or so you keep the W and you interpolate the W across the triangle and then divide at every pixel, and then you'll get the correct perspective location of the texture at every pixel.
Does that?
But you can look that up. It's called perspective divide.
Yeah, well, which is
perspective correction.
Okay, and I had gone through and did a lot of different research on it, and I found different points that talked about the issue after I had actually entirely recreated it and proved that it happened. I was actually thinking when I was doing that originally with this, and they was getting this distortion across this point, that I had a math error in my interpolation. And it took me a long time to understand because I was going to the exact 10% on there. And I will have to think through your solution of that, doing the perspective divider, the W divide later, and interpolating all of those. I will have to try that and see that. Yeah. And of course, you know, I did call it graphics for dummies. So I am not an expert on this. So, yeah. But thank you for that clue. So. I want to go back to this math a little bit here when I'm creating the world, just to show people kind of how simple this is. I just take a model, I scale it, I multiply that model by rotating it, and then making three separate models. Take a world, take a model, which is a mesh, and multiply it by this matrix, which is the rotate and transform, X, Y, Z, and the X again, and just adding these up, adding them to the world. Then I do my point of view, my field of view, my viewport, and my perspective divide, which apparently might work out better if I did that later. That would actually save me an entire step here. However, I'm going to have to do how many ever 111 million divides once for each pixel, or 3 times for each pixel. So it's not that you have to recompute every single point every single time and do excessive. I don't have to multiply this model times this matrix and then that result times this matrix. This is a combined matrix. And so are these 4 terms here. So I'm really only this this multiply here is as complex as any of these, even though I'm doing 4 different matrices, because these are all combined in order. And this is the magic that does the point of view, field of view, and viewport. And that just these matrices in order, point of view, field of view, and view multiplied by this give me the screen coordinates. If you do these in the wrong order, your world will look massively confused, because this is first world times point of view, world times field of view, world times view, is effectively what it is really doing. Actually, I say world times point of view, that result times field of view, that result times view, and then I do my perspective divide and return the screen. Okay. Teams is fighting with me. So more questions or critique or suggestions? I like that one suggestion about doing the perspective divide, the W on each one. That might help with some of my problems.
Well,
actually, I think that would that actually?
It's super expensive, but like.
But it actually affects that, corrects for the interpolation error.
Yeah. So the problem is you're interpolating in screen space with your method, and you actually want to interpolate in model space or whatever, or world space. And so
okay.
So you have to interpolate the W across the triangle and then divide. But you can also do tricks like only calculate the W like every 8 pixels or something, and then use the same W. Like when you're going across a span, you break it into 8 pixel chunks and only calculate the W for each of those 8 pixel chunks. So that way you're doing, and then, you take the reciprocal, so 1 over W, and then multiply, because multiplies are much faster than divides, like 30 times as fast or something. So there's a lot of tricks. There's a million tricks in graphics.
Yeah, there's an entire subject I did not broach, which you probably know about. When you're doing the rasterization, a pixel in what is on the screen, if you take the corner coordinates of that pixel and you map that back to your original texture, your source image, that may actually map back to covering 9 or 10 pixels, or some big portion of pixels, and you might have to do some color averaging to figure out what the weighted average is for that. It may not even actually be a regular rectangular shape, and you might have to figure out portions of it's 90, it's 30% of this pixel, 20% of this pixel, 10% of this pixel, and then average those colors. And you also have the reverse problem of what if you're actually, for every pixel in the rasterization you're going across, it's really just reading from the same pixel over and over and over again. You could simplify the interpolation of looking back and forth if you figure out where does this pixel start in my screen on my raster and where does it end, and the pixel from the original texture source image, and that you want to apply on there. So you'd only really have to look it up once, and you just draw it n number of times for that raster.
So yeah, that works as long as you don't have perspective. But
yeah, there's
so like usually, like, I don't know how you're doing interpolation, but you can pre-calculate. Like if I'm interpolating across a thing that's 100 pixels wide, I can figure out what the delta is per pixel once, and then I just have to add that one time. Just do an add at every
problem pixel. With that is, well, you'd have to keep them in floats. And actually, internally, I was actually dealing with everything in floats, not doubles. Floats are more typically used in graphics because you get more in memory at a time. At least that's as I was told. And it covers pretty much your entire coordinate system with a lot of detail. What you were talking about there is if you calculate just that for each pixel, what the horizontal and vertical step is on that, for the interpolation, you get a cumulative error. And by the time you get to the end, you may actually be off by a couple pixels. Even though we're in a float, you're going to have some small accuracy issues. If it were straight floats, I promise, straight integers, you're really going to have a hard time with the math on that. But of course, we're dealing with everything in floats. So,
yeah, getting it's really difficult to get rid of all the aliasing problems. Like I noticed on your cubes, there's black lines along the edges, right? And that's super hard to get rid of.
That's
Very
actually
difficult.
a halfway of an off by one of where the different surfaces meet up together on corners. There's also what we talked about skipping a lot of the vector math that's happening and reflections and that type of stuff. When you get the light source coming and shining on a surface, you have the same issue of you really only know what those angles are on the corners of your triangles where each of those points are. You would have to calculate what the reflection angles are there, and then also you would effectively have interpolation entirely between all the sides of calculating what the amount of reflected light is.
Yeah.
Because on the close corner to the light source, it's going to be a one angle, and on the far corner of the triangle, it's going to be at a different angle. And so the light reflection, you'd have to kind of interpolate between there. I didn't bother doing any of that math because it becomes even more of a more complex problem.
Yeah, so basically you end up having to do everything per pixel, right? So calculating the lighting, calculating the texture, dividing by W, it's all per pixel to get it to look exactly right.
Yeah, and as I talked about,
guys.
What was it, Robin?
Feel free to continue, but I will stop recording, all right?
Sure.
Okay, thank you very much.